Hello, my name is Andy, and today I will be presenting my Underactuated Robotics final project, Estimating Payload Physical Parameters. We define the physical properties of a robot's payload as the mass, center of mass, the inertia tensor, and coefficients of friction, although we won't be focusing on those in this project. These can be used for trajectory optimization, controller design, identifying a product, if say in a warehouse scenario, or avoiding hardware damage by running against the robot's torque limits. We set up the system as a 7th degree of freedom KUKA Iwa robot arm, with the grasping of the object represented as an additional joint attached to the 7th link, like a pendulum. We began experiments with a mustard bottle object because it seemed to have an interesting shape. The system is underactuated in that we cannot directly control the angle of the mustard bottle. We can use data collected by the robot to find these values using the lump parameter decomposition. The equations of motion of the system have a cool property that they are affine in the lump parameters, or linear combinations of the parameters we want to estimate. This works for the parameters of the mustard bottle too. This form allows us to use least squares to find an estimate of these parameters. Luckily, the parameters of our system that we want to estimate decompose very nicely. We log the joint states and torque command information from the robot along samples in its trajectory, populating the data matrix that will be used for least squares. This was the first trajectory we tested for data collection. It represents a typical trajectory for a pick-and-place task the robot might want to accomplish. Here are the results of the mass and center of mass estimations as the robot's trajectory is simulated. With a closer look, you'll notice the results are mostly terrible. Let's look at the results of the inertial parameters, which require high precision. Again, they are not good. Here's a closer look at the moment of inertia along the z-axis. It is incorrect by 4 orders of magnitude. Interestingly, the estimate does not settle until long after the robot has stopped moving. This trajectory of the robot shows why this is the case very well. The object doesn't settle due to there being no friction in the joint. We actually see very accurate results for the mass, which was the main success of this project. There are many reasons why the other values could have been calculated incorrectly. In experiments, we saw high variation in the estimations depending on the trajectory the robot took. An initial goal of this project was to formulate a trajectory optimization to maximize the expectation of these parameters, but this proved to be computationally challenging in Drake. Most likely, the system needs a thorough debugging, but we believe the method is sound based off of existing literature and the results from the mass calculation. Thank you for listening to my final project.